Hello, everybody. Thanks again for taking the time and joining our Mechanical Seal Support System Tech Talk. I am Ethan Liebswager, and I'm with Swagelock, Minnesota, North Dakota, and Appleton as an application engineer in our Custom Solutions department. I just wanted to make a quick reminder again that unfortunately we won't be able to hear anybody or stop the presentation for any kind of questions, but definitely leave a question in your name in the question and answer form, and we'll answer anything we can at the end. Or if there's something pertinent during the presentation, we'll try to answer those during. Thanks again for taking the time. I just want to go kind of through, really the presentation is looking at how Swagelock can help you with your mechanical seal support systems and really tackling those challenges that are out there on a daily basis. This is something that we've been doing for a number of years, and we really formalized the program in the last 3-4 years, really taking into any scope changes that API 641 has made over the last 5 or so years. The first place to really start ends up being, what are we really trying to do for you? So very often out in the field, we've ended up seeing these type of systems that are traditionally all pipe connected to a pump, which is a huge source of vibration. And even though you end up with supporting the best that you can with these pipe systems, NPT is just known for leaking, especially under high vibration. On top of that, making things worse is that due to some of these complex support systems and the amount of components in there, you end up running into a lot of installation challenges, using a lot of union nuts. NPT just naturally will increase the amount of leak points that you have and threaded connections. And then when it comes to remaking or redoing anything on the pump, becomes a nightmare for maintenance folks that essentially end up having to take apart the entire piping system. So in this case, what you're really looking at is pump out in the field. And in this application, they had to take off the head of the pump, which required most of the disassembly of the entire piping system. When they ended up getting it torn apart, essentially they ended up with all these piping components that effectively weren't usable anymore and had to be remade. Again, just due to the nature of pipe, you end up with pretty much a mess for any of your installation folks, even when not particularly touching the seal support system. This is generally just doing maintenance with the pump itself. A solution that tubing can really help out is, in this case, tubing's available anywhere from 1/16 inch all the way up to 2 inch. Typically, these seal support systems we end up seeing in that 1/2, 3/4, 1 inch range. And in this case, they were able to retube the entire system, really bending the tube as much as possible, which provides a lot of advantages with mechanical seal support systems in general. Due to pressure drop, but also it eliminates a ton of leak points. And anytime that you can do these kind of bends, that type of thing, disassembly and taking components out also makes their life a lot easier when taking off this seal or the motor, for instance. You can pull off just a handful of lines and actually access what you need to access. Another good example of what we've seen out in a lot of refineries is this ends up being a Plan 54 system where the entire seal support system is completely separate with a reservoir. Again, with pipe and flanges and weld, it ends up being, again, a maintenance nightmare for any time that the seal support system has any kind of issues or component replacements that need to be done. And you can see just how dirty, especially with some of these hydrocarbon seal fluids, once it starts leaking, it can really make a mess in that area around the pump. Once you get it cleaned up and can tube as much of it as possible, you really do end up with a nice compact system. It's considerably lighter, and the big thing that we've noticed is because tubing doesn't take up nearly as much space too, it's a lot easier for personnel to be working around the components as well. When you really look at from a component provider standpoint, you can make these tubing systems really compact. Again, it takes off a lot of weight, so even shipping some of these sub systems becomes tremendously easier, because for the most part, it ends up being all about the pump, and the support system has to be there, but you don't want it to be the part that's actually taking up the most space. So when we look at traditionally how maintenance and rotating equipment departments have handled pump maintenance over the year, a lot of times you end up with some type of Excel spreadsheet that is tracking pump failures and downtime out in the system. And really the point of this is to really find those bad actors out there and really concentrate on fixing the pumps that are giving you a lot of issues out there. I think it's really important to remember with pumps, really what is the good amount of our failures, and a lot of our failures end up coming from two parts of the system. Roller bearings has been a hyper focus of especially rotating groups for many years, and they've gotten very, very good at eliminating quite a few of those failures over time. One thing that was ignored for quite a few years, up until maybe the last 10-15 years, is the shaft shield components. If you can control the roller shaft seal components, you end up with about 2/3 of your pump downtime can be eliminated or at least controlled. When we look at some of the industry standards out there, your typical average pump is probably most departments would average about 70 months on there. So even if we just say that you have a fair system where you're getting 62 to 70 months, anything that can get you into that very good range, let's say an extra 12 months, that's a whole year's worth of downtime that you don't have to worry about. And one thing that I really like to point out with this is that you'll notice that seals definitely end up being the piece that ends up being the majority of your downtime. Couplings and bearings are again a close second, but in most cases they don't end up causing you nearly as much issues as that seal component. So the way that the petroleum industry ended up trying to handle this back in 1994 was coming out with their first revision of 682. Really, the standard was created all around your mechanical seal support systems, and truly, how do we provide the pump with exactly, or that pump seal, mechanical seal, with exactly what it needs to get the longest longevity out of it. It's important to note that API 682 is a standard for best practices, but by no means is it required for specifications. The main reason for that is you don't see the same application over and over. Every pump will have different attributes to it, and it's impossible to say that you can have this one plan for this type of mechanical seal every time. The reality out there is there's certain things that you'll need to do with that seal to make it work. So it's always try to follow your best practices, but by no means can you not deviate from it. And that's really what we've focused on, is when we have to deviate from these plans, being as flexible as possible. The other big thing that the standard did too is it created a standard terminology for suppliers, plant personnel, maintenance folks. When you looked at some of these old systems, again, traditionally these were pipe systems because everything is beefy, so I'm going to use beefy pipe on this. So a lot of times Schedule 80 was very common, 1/2 inch, and I see a lot of 3/4 pipe systems out there as well. The issue with specifically mechanical seal systems is because again it's around the pump, everything's vibrating. Threads have a lot of issues sealing in vibration systems, and pipe just naturally adds a lot of leak points in the systems. It gets very, very difficult to use pipe, especially as you get closer to the pump. So leak points become a huge issue. And then another thing that is definitely forgotten about with some of these thermal siphoning effects that you may see on some of the seal plans, 90-degree elbows are also not preferred. You can cause a lot of pressure drop through systems, and that can cause just naturally a lot of problems with how some of these systems are supposed to work. So large radius bends are always preferred over 90-degree elbows. Also, carbon steel has been the standard, but would end up on a replacement schedule, which isn't ideal either. So as API 682 has tried to revise this, back in 2004, they came out with the 2nd edition. Really, they recognize the fact that the 1st edition only took a narrow scope of really liquid seals. With the introduction and popularity of gas seals over the years, that was the biggest add-in that they did, while also realizing that there's definitely some non-contacting, some of your dual seals, and especially leakage containment. So with these gas seals, it's actually one that we've been doing for probably 30 years. We just didn't know it. So a lot of times plant personnel are buying these components and installing them in to deliver gas to the seal. One thing to really kind of take note is these systems just kind of get put up. There's no real rhyme or reason to how to control them from pump to pump. So they end up being hard to control, hard to maintenance, really troubleshoot even. And it can be very confusing to an operator that has to control this. And all of that ends up affecting the seal. The seal just may not get provided with the required flush that it needs. So when you look at now what we can do is, it's not that much different other than for the fact that now you have that regulator to control pressure. You have the gauge to easily read the pressure. A big thing too is if you're running off a gas bottle, it's probably fine. The gas is probably clean enough. But if you're running off the nitrogen, house nitrogen system, there may be moisture, there may be debris, so filtration on the panel. And if you have a filter, that means that they have to be checked and or replaced every once in a while. We've even added bypasses and that type of thing. Having flow control is obviously a huge piece of this. So it's giving the operator the ability to control while also not forgetting about those maintenance aspects that are naturally going to go into this. Lastly, API 682 came out with the 4th edition, and this is really what opened the door for Swagelok to be much more involved with these systems, with the addition of adding tubing to the spec. So the 4th edition actually has a recommendation for tubing. When you look at that tubing, it's in the 1/2, 3/4, and 1 inch, which is the recommendations generally for mechanical seal support systems. And they made an interesting point is you'll notice that these minimum wall thicknesses typically end up being towards the thickest walls that you can use in a compression fitting. The majority of the reason for that is there's a realization by API out in plants that no matter what you do, these systems are going to be used as handrails and foot rails and ladders by plant personnel. And plant personnel were used to these pipe systems that are structurally very beefy. So they noted that you should be trying to put in the heaviest wall tubing that you can, knowing that operators are going to do what they do. There's really no way to prevent completely that. And at the same time, this gives the best chance of reducing failures with your mechanical seal support system. Because of the addition of tubing in these systems, that really allowed us to right away come up with kind of 4 innovations that seem fairly simple on the surface, but have been actually some of the most popular parts of our plans. The first is looking at what we call an extended male connector. So very traditionally out in the field, you end up with pumps that will have this thread connection going into the pump seal. The issue with this connection is typically there's some type of shroud or kind of support system around it that is either required for support and or protecting the rotating components in the pump. So you have to clear that shroud. So we can't just take a normal male connector tube fitting and thread it in and hope that it's going to clear those shrouds. So typically the way that this is always done is you take a pipe nipple, usually 4 or 6 inches long, and you'll thread it in, and then you'll end up with a female connector, or a lot of times I even see a pipe coupler, and then you'll do a male connector because that's what's you stock for sway jaw components. Not everyone necessarily has a female connector even. So you end up with 1, 2, 3 potential MPT points before you get to your compression fitting. So what we did is we came up with the idea of, well, we can just make an elongated male connector. So essentially what ends up happening is we take that 1, 2, 3 MPT connections. We basically do a bar stock where you only have the MPT connection into the pump because there's no way to really eliminate that connection. And then you get the clearance that you need from the pump, and then you can run your tubing from there. So where some of these seal systems easily will have 1, 2, or 3 connection points, you can eliminate potentially up to just 6 threaded connections right at the pump connection. Another thing that was a realization is it's great to do a hex along the entire way. The reality is some of these pump housings are really, really tight and really are only set up for that pipe nipple. So what we did is then we can machine off basically that hex shank. They've even revised where they beefed up the end hex to give you, again, that male extended connector that can work in any of these systems. Currently, we only make the 4 and 6 inch connectors because that is pretty much the standard out in the field. Moving on to some of the seal plans, what you're going to find very quickly is that orifice fittings, usually the 0.125 orifice, is very, very common in these systems. So when you look at how these orifice fittings have been done out in the field traditionally, is you take your flanges, whether it's a weld or typically I see, again, threaded NPT flange connectors, and then you take your orifice plate and bolt that all together. One issue is flanges are very heavy, bulky, and especially when they're going to be hanging in the middle of a tubing system or even your piping system, that's a lot of weight that typically is going to go unsupported. And in some of these systems, you may find where you have 2, even 3 different orifice points. So what we're able to do is we're able to take this flange by orifice plate connection and really build it into just simply our tube fitting technology. We've actually offered orifice fittings for a long time, and really what we're doing is we're putting a plate in the orifice with whatever required E dimension. Again, the standard would be 0.125 unless we're told otherwise to do a different E dimension. And really the kicker for us is if you're stocking a bunch of union fittings, we want to make sure that an operator doesn't grab a union fitting without an orifice in it, or they grab the orifice fitting for a different application and then they end up with reduced flow. So it's very, very important that we add this identification tag, calling out either a restricted orifice or that orifice size. So that way there's no mistaking the fact that this fitting is different from all the other 30 unions that may be sitting in the stock. When you look at some of these applications, you'll see where the flanges are actually running right off of your discharge or feed lines into the pump. So if you have an integral flange off of there, that's great. What we can do is, instead of adding a flange, probably with your NPT connection, having a pipe system through an elbow, and then having your orifice plate, what we can do is we can actually build it all into one machined piece and run tubing directly out the back of it. So again, we can set the orifice fitting through the flange, and just like the other ones, we want to make sure that someone doesn't grab a normal flange adapter by accident. So we'll make sure that it's restricted bore with the orifice size, and that also gets printed on the edge of the flange as well. So there's actually two ways of identification of these. So even when we look at new installations, we find some interesting things, and you can start to imagine, even with something that's been built in the last 5 years since API, the fourth generation, came out, you will end up seeing some of the advantages of this. So when you look at a very typical flange orifice fitting, again, you end up with the flange with your orifice plate through it. In this case, they ended up welding on that side, and then you end up with two of them. When looking at the male connector side, very typical, you have your pipe nipple. In this case, they actually used a reducer to get up to the 1/2 inch, which that would be also unadvisable just based on the pressure drop that you may see with this, especially on this application where you're probably running some type of thermosiphoning effect out of the cooler. And the other big one too that API 641 has said is they don't recommend hoses out there just based on you're going to have a much lower mean time to failure with hoses. They almost always are going to recommend using pipe. Now, in definitely certain applications, you're going to end up seeing hoses. In that case, it's just really, really important to make sure that you're treating the hose the best you can, because let's say this was in service for 2 years, that hose probably isn't going to make it much longer based off of the look of it and the fact that you're not even giving a recommended bend radius to that hose. Taking some of those concepts and knowing that a lot of these seal plans may require some type of pressure measurement as well. We've even gone as far as building your orifice adapter off of your discharge line and going to a T and putting in your gauge measurement, trying to eliminate having that type of equipment also hanging off the tubing. Ideally, you would end up supporting this tubing like you normally would. In reality, with the seal support systems, it's very, very difficult to even find mounting points. I've seen some really, really ingenious ways to do it, but anytime that you can take some of the stress out of the middle, because really, in the end, all of this is going to be vibrating. So you want to try to secure and move the heavy components as close to things as possible. With that said, the one thing that does end up getting added quite often, and one of the rules with seal support plans, is I have to make sure that I have the proper temperature of my flush going into that seal chamber. Typically, if it gets too high, that can cause early failure on my mechanical seal. So it's really, really important to have some type of temperature indication, which is usually the first indication that something is wrong in the seal support system. When you look at these temperature indication systems, they can get very, very bulky very, very quickly. Due to the Thermowell that ends up having to go into these systems, like this piece here, you end up having to oversize that T area to get the Thermowell to fit in there. So even though that they use a compression fitting here, they ended up with 1, 2, 3, 4, 5 different welds just to get where they can thread in their Thermowell, and then they can put the thermometer in the Thermowell. One issue that we've also heard out in the field is when you tell an operator to go replace the thermometer, sometimes there's a safety risk of accidentally disconnecting the Thermowell rather than disconnecting the thermometer. In this case, it's really deceiving because they ended up putting tape on the Thermowell side. So this end connection, or this connection, ends up looking identical to this connection, and you end up causing some type of safety hazard. And you can see it even gets a little bit worse once you start doing flange connections on the Thermowell. So what we're able to do is we're able to take these very typical stacked type connections and really turning it into essentially a one-piece connection. So what I can do is I can take the tube fittings on each side of a T. Typically, I end up seeing the straight pattern, but we did also make an angle pattern for certain situations. And what they did is they put this Thermowell in there, and they actually made a weld between the T body and the Thermowell. So there's no way to accidentally thread out that Thermowell connection out of the T, causing an uncontrolled release of the seal fluid. Then you simply just thread in your short stem 2.5-inch thermometer, and you end up with a very, very compact system for these thermometer applications. Because again, remember too, where these are probably getting put in is right next to the fluid input into the seal. So very typically, these are going to be hanging in the middle of the seal fluid line, and this type of stack adds a tremendous amount of weight compared to what you potentially could get out of the Thermowell Tee that we've developed. Another thing I really like to point out is when you look at a lot of these seal plans, it looks like even on a plan 32, all of these components are just kind of hanging in the line. So you end up with your thermometer, temperature control in there, and then you end up with a pressure gauge. You probably have some type of flow controller and flow indicator. If it's a dirty fluid, you'll definitely end up with some type of filtration. A lot of times you can't allow anything to back up into your system, and I almost always see the shutoff valve way up in the pipe rack 20 feet above your head. For easy control and troubleshooting, it's nice to get that at an operator level where everything is nicely on one panel, easy to track and maintenance. So again, kind of using the concept of anytime we can use two bend loops, being able to easily pull components off and maintenance them or clean things out, depending on the system. And as well, knowing that there's certain components for these plans that are typically required, and we've tried to come up with even simple concepts as bypass loops around filters, just so you don't have to take the pump out of line to maintenance the filter or clean out the filter. And how do I know the filter is getting dirty? Just differential pressure across the filter. There's little things like that that we've introduced in any one plan. A few recommendations that may or may not be needed for the application that you have. If there is something even more specific to the requirement, we make these locally in our Chaska office, and we're always able to customize and put in what's required for that application, while still trying to maintain really that emphasis on the maintainability and maintenance aspect. When we get beyond API 641, there was also a few things that we've noticed over the years with these seal plans, and probably one of the coolest things that we've just ended up incorporating into our seal pots is some of these refilling systems. So when you look at typically how this was done in a plant is if it's a pressurized seal pot, of course that has to be depressurized, opened typically on the top, and someone has to go on a ladder, hopefully a little bit more sophistication than the funnel and bucket, but I've definitely heard where people are on a ladder with the bucket, respirator, and pouring it into the seal pot while somebody's watching the line. It's very cumbersome. It's actually very costly because you have to take the pump out of service, and I think it gets to a point of if you have 30, 40 seal pots that are running, it becomes someone's job every day to just go around and fill seal pots. So one thing that we really want to look at is how can we reinvent the system that will make it easier to do it? When we look at what's the easiest possible way, well, ideally the filler would end up, or operator would be able to do this all at ground level. So how can we bring pouring the liquid into the top of the seal pot to ground level? Well, simply adding some type of fill tube to the end of the seal pot makes a lot of sense in this sense. Whatever you end up needing for isolation gauges, double block and bleed, we can provide that. And then typically what we'll end up doing is we will use some type of quick connect system off to the side so that you can just have your fluid pump connect into the system and fill the seal pot while watching your level. Everything is done at ground level and in theory with no leaking. And I know there's cases that people don't even have to take the system out of line. You can just do this and keep the level without even switching the pump over. We've also made the seal pot pump systems and refilling systems. So definitely, if there's any questions with that piece of it, we've come up with multiple different sets of seal pot systems. So that is the majority of the presentation. I just want to go quickly through our application guide. I want to encourage, if you do have any questions on anything, please enter it now, and we can cover any questions that have come in as well. So anything that you have, please go through that piece of it. And while we kind of wait for people to do that, again, I just want to kind of cover what are we doing with the application guide. So as we looked at API 641, they called out, I believe there's 60 plans, 60 some plans that have some kind of standards. And some of them are obviously simpler than others. So you can get kind of a depiction on like a plan 14, where you kind of just have the inlet fluid line, and then you have your outlet fluid line coming from your inlet and discharge, as well as that plan 32 that we kind of saw earlier, all the way up to a complicated 55 system where you have a reservoir, pump, and a lot of required equipment with the system. We can kind of call out all the general things that API 641 has for recommendations. And with a lot of these systems, we try to incorporate as much as possible what the plant is doing as well. We don't want to add something in that's another part or another maintenance nightmare for the plants, because we know that you have enough of those the way it is. When we look at how we kind of set up the application guide, it ends up being kind of falling in two categories. We have kits, which ends up being kind of all the tubing that goes from some type of stand-like system. So the idea of this was, it's really, really hard to know exactly what you're going to need to connect this. In a lot of ways, these have to be field installs in some way. So what we can do is we can kit all of your high point, low point vent systems, all your thermometers and thermowells right into your extended male connectors. We can kit all of that so it's easy to install out in the field. Really, all you need is a bender and some tubing, and you should be able to install this in much quicker than what you would end up with a pipe system. As we look at some of, especially the seal pot assemblies and some of these 55s, then we can actually look at doing the entire assembly, looking whether it's third party, whatever plant standards you have. Of course, the 4th generation 2 is actually calling out much more transmitters, even over rather switches. So we can be very, very flexible in what you're currently using while trying to implement some of these advantages that we've seen over time. So when we look at kind of what that looks like, you end up with basically this kind of 84-page document that goes through each individual plan that you would see out in the field, as well as any kind of other supplemental information for anybody that's not as familiar with API 682. And of course, if you have any other questions or kind of want to consult, I'm more than willing to come out on site and kind of look at what you're doing and what you're trying to achieve in the next 5 years.